saw in the previous lecture a very important article, but now you can see that we can resolve some of its limitations using this clustering-based inference. And of course, my focus is in biomedical text, which is very interesting. And so let's focus on this article in 2021 from Zuckerberg Initiative Company as well as the UMA. The motivation is that due to a large number of entities in biomedical text, only a small fraction of entities have corresponding labeling data. So then this necessitates entity linking model, which are able to link mentions of unseen entities using line representation of entities. Previous approaches link each mention independently, ignoring the relationships within and across documents between the entity mentions. So this reminds me of the factor graph. In factor graph, we try to model all the constraints. So it's like a structured prediction problem. This is again a structured prediction problem, but they don't do it like what we do in probabilistic factor graphs and those probabilistic graphical model. We do it like here, very, very deep learning type idea. And the idea is that they introduced a model in which linking decision can be made not merely by linking to a knowledge-based entity, but also by grouping multiple mentions together via clustering and jointly making linking predictions. They propose an entity linking model in which entity mentions are either linked directly to an entity in the knowledge base or join a cluster of other mentions and link as a cluster to an entity in the knowledge base. Some mentions may be difficult to link directly to the referent ground truth entity, but may have very clear coreference relationships to other mentions. So long as one mention among the group of mentions clusters together links to the correct entity, the entire cluster can be correctly classified. So this is an example. So you can link this mention facial expression to this entity. We can link this mention to this entity, but we don't need this mention. We don't need a training data that links this directly to this entity. We can do it indirectly. So there are several intermittent variables that we can take advantage. And that's the beauty of that, because capturing the context, the representation of the text, and make advantage of that. So this is important for discovery. This is very important that we have two kinds of learning. Each one has pros and cons. For example, the problem of transductive learning is that, first of all, it can become very computationally expensive. If new unlabeled points are encountered, we will have to rerun the algorithm again, even for one single test, single new thing. So it's a big problem. We are not used to do it. This is what is classical machine learning, what we have used to do every day, inductive learning. We build a predictive model, but it has some problems, of course. If new unlabeled points are encountered, we can use the input build. This is good. But train a model on labeled points which we have never encountered, and of course it is good that it is less computational cost. So each has pros and cons. That's why I always think about a new paradigm, which has a bit of both worlds, which is a little bit inductive and little bit transductive. It's a hybrid version that I'm working on. So the inductive mode, as I said, the training and inference are totally different. For transductive, even one new thing, even one new entity changes all of your training. You should do it from scratch again. You should start from again. You cannot take advantage of something like transfer learning. You cannot do domain adaptation. You cannot do anything at all. And so we have some mentions, we have some entities here. We want to cluster them and first, if we want to do it independently, this becomes like this. But we will define some constraint here. So the clustering-based entity linking, whenever every cluster contains exactly one entity, this process can no longer merge any clusters and thus terminates. So our vertices of your graph, some of the vertices are for mentions, some of the vertices are for entities, and we want to learn these these functions, but they are parameterized, so we can learn it easily. And for the weights of the, for example, from mi to mj, from the weights between these two nodes, this edge has a weight of w. Or similarly, from mi to el, entities and mentions, we have this another weight. And so it's a beautiful process that we go from, first we have just entity and mentions, and then we combine, we grow. And so the affinity models that they use is this. First you have this token to saying this, and then mj, I mean the first mention, because it's not just single mention, we are doing it structurally. It's in harmony with structured prediction, because mi and mj are linked together, and for each of the mentions you care about the left context and the right context, and of course your mention is here. And why do I emphasize on this start and end tokens? Because hierarchically in the higher dimensional space it understands, I mean, it fine-tunes correctly, and it avoids overfitting, and also it recognizes the importance of each bit of information. And so we add also the description of an entity. This one is interesting. I mean, description, we use it for zero-shot learning of for link prediction, for entity, for relation prediction, relation extraction. And so these descriptions are very valuable because you can define it very quickly. And when you don't have unseen data, in the context of zero-shot learning, you have to take advantage of these important descriptions. So the algorithm is you construct these edges, you make it bigger and bigger from these mentioned, and you know the distance between them, the similarity between them, and even between mentions and entities, and even from mentions to mentions, as I said. So we make linking decisions based on clustering. And our training, we explain the training procedure for the affinity models. We have two models for mention, and mention entity. And so we have this loss that we use this max margin, usually with margin of mu. This is your margin, because we want our problem to be robust, our solution to be robust against noise. That's why I use max margin. We want to have less negative things, and we have to have more appreciate positive things. We don't like negative samples, so this is how loss is formed. And for mention entity, but we use a triplet max, like before, triplet max. So we have A, and then negative and positive. We want we don't encourage this one, but we encourage this link. We encourage this one, we increase this, we reduce the other one. And we have some data sets, med mentions, and BC5 CDR, which is another entity linking benchmark in biomedical text. And this is an example. For example, you have PubMed abstract, then you have you link each mention to this entity, and then you cluster them, and you even extract some new entities.